Class example 2.16 revisits the problem of creating a box out of a sheet of cardboard. But this question is significantly trickier. And the reason is the diagram is less straightforward, and there are implications regarding how we treat the domain. So let's jump in here. We have a box with a lid being created by removing two congruent squares from one end of a rectangular piece of cardboard. The cardboard measures 8.5 inches by 11 inches. Now, the blue rectangles you see will be cut out and removed, so they will not be used in the box. That's just waste. The tricky part of this is we have to understand, unlike the last example where we had a square from each corner and our length and width expressions were dealt with the same way, here it's a little bit different. The width of the cardboard sheet will actually become the length of the box once it's folded, because that 8.5 is longer than the 5.5. That 8.5 inches is being decreased on either end by an x. So the new length of the box will be 8.5 decreased by 2x. However, when we look at the side that was originally 11 inches and is now separated into two sections of 5.5 inches, it's actually only being decreased from one end, the left end in this diagram, which means that its expression will not be 5.5 minus 2x, but rather minus 1x. And this can be the trickiest part, is people assume it will be like typical box questions where all four corners are cut out. So be really careful there. Now we can picture that when this is folded up, we have 8.5 minus 2x, 5.5 minus x, and then our height of x. This gives us our expression for volume because it is length times width times height. And from here we will proceed as with the other question. Putting this in our calculator, we again get a graph that exceeds the window settings. Notice it is a cubic. However, once it is dipped below the x-axis that first time, nothing to the right of that is meaningful within the context of the question. We will identify that a window with a maximum of 35 will be enough for us to capture that first local max. Again, there's no reason to get so well fitted. If you had a y maximum of 50, that would certainly be appropriate. Here, if your y maximum was say 1000, that would be less appropriate, as you're not using a significant portion of the screen to see the major features of the curve. We'll calculate the coordinates of the local maximum that happens and find that at an x coordinate of 1.59, we generate a height of 33.1. We'll also determine that we have x-intercepts at 0 and 4.25. So our 0 is indicating that we must cut more than 0 as in terms of the length of the square in order to generate a box of positive volume. And our 4.25 states that once we've cut 4.25, we no longer have a box, or we have a box of 0 volume, and beyond that, we have a theoretical box of negative volume. This question is made much easier by good habits. And one of those habits is labeling our diagrams. You'll notice here that I've labeled the x-axis as length cut out and have included the units of centimeters, given that length is a linear measure of degree 1. And on the y-axis, I've labeled volume with centimeters cubed, given that volume is a cubic measurement of degree 3. That means later when I'm referring to my values, like the 1.585 and the 33.1, I'll know what their units are. So here, we can state our domain as being between 0 and 4.25. We've already discussed how less than 0 we have no box, greater than 4.25, we have no box. And again, I'll put a star beside this one because the 4.25 restriction in this case came from the length, because the 8.5 minus 2x was more limiting than the 5.5 minus x. And you could figure that out because 5.5 minus x doesn't become 0 until x is a measure of 5.5. We see that our x coordinate of 1.585 in units of inches gives us our maximum volume. And at that point, we have a max volume of 33.1 inches cubed. Earlier, I think I misspoke. I mentioned the units being labeled in centimeters and centimeters cubed. I should have said inches and inches cubed. Now, the question here asks us to state the dimensions yielding this maximum volume. This is really important. Where does that number 3.915 and 5.33 come from? Well, x being 1.585 generates the maximum volume. We determined earlier that our expression for volume was 8.5 minus 2x times 5.5 minus x times x. And so if we rewrite that and we replace the x's with 1.585, we'll find that 5.5 minus 1.585 generates 3.915, and that 8.5 minus 2 times 1.585 gives us 5.33. So those are the actual measurements of the width, length, and height that multiply together to make 33.1 inches cubed. I hope with that you feel confident and ready to try the practice problems.